Here is a typical structure of a polymer. In this case, highlighted in the blue, you will see 2 carbon atoms and 4 hydrogen atoms. So the basic building unit is referred to as a monomer, in this case ethylene, and when you have many of them, it becomes polyethylene. The way polyethylene is synthesized is there is a double bond, and this particular monomer is ethylene. When it's zipped together, you get this large molecular weight material. In general, polymers can be synthesized by 2 typical methods. One is called addition polymerization or chain polymerization. The second is called step polymerization, a variant of which is condensation polymerization. In the first case, you have a bunch of monomers. You add an initiator to start the reaction wherein all the monomers rapidly begin to connect to each other in a growing chain. You finally stop the reaction by a termination process to cap off the growth of the chain. In the second case, you have a monomer. The monomer itself might have more than one reactive groups, or you could have a mixture of monomers with two or more different reactive groups. They begin to react with each other and begin to increase in molecular weight. In contrast to addition polymerization, the monomers get used very rapidly. The polymerization itself is a much slower process, and to get chains, high molecular weight polymers, takes a long time. You usually end up having a distribution, a large distribution of species at various stages. The reaction really never stops. Examples of addition polymerization, the first method, include the polyethylenes that we saw earlier, polypropylene, polyvinyl chloride, polyisoprene. And then the second common class of polymerization, step polymerization, you have examples such as nylon, polycarbonate, and different polyesters. We talk about polymers as materials with large molecular weights rather than something that is present in a lower molecular weight material where all the individual molecules are in exactly the same molecular weight. So this distribution has important consequences. Depending upon defining that distribution, you could get different properties. Higher molecular weight results in increase in mechanical strength. That is one direct correlation. The other change that occurs is the chains become harder to move in the molten state, and so the viscosity increases in the fluid state. This is mapped out nominally where property is plotted against molecular weight, and you can see tensile strength in this case goes up with increasing molecular weight. So does the melting temperature. This plot over here of temperature against molecular weight. Very low molecular weights at low temperatures are mobile liquids or even gases. Propane, butane, liquids, diesel, gasoline, and then you go into crystalline solids, waxes, which can melt into a liquid that's a little bit more viscous than, say, gasoline, for instance. As you go to very high molecular weight, the ability of the chains to be able to collapse into an organized lattice of a crystal reduces. So you end up getting partially crystalline materials as opposed to fully crystalline materials. As you raise the temperature of this high molecular weight materials, it becomes more pliable. It goes into a tough phase and then a rubbery phase. And so this interplay between molecular weight and temperature are important to understand. We'll explore more of it during lecture 2. Let's try to identify some of these thermoplastics. So we first saw polyethylene as 2 carbon atoms surrounded by 4 hydrogen atoms. If you replace one of those hydrogen atoms by this group over here, CH3, which is also referred to as a methyl group in organic chemistry, if you remember, then you have the repeat unit as propylene and the polymer as polypropylene. Instead, you replace one of the hydrogen atoms in the ethylene repeat unit with a chlorine atom. You get vinyl chloride as a monomer and the polymer as polyvinyl chloride or PVC. Finally, you could replace all 4 of those hydrogen atoms with other fluorine. You get tetra 4 fluoro polytetrafluoroethylene, PTFE, commonly known as Teflon. Let's try some more. This one, polypropylene. We've seen it before. If instead of the methyl group, you change it with this benzene ring, you get the monomer to be styrene, and polystyrene is the polymer. Styrofoam is a common name you might be familiar with. If in propylene you replace one more hydrogen atom by this group over here, which contains oxygen and carbon and hydrogen, you get methyl methacrylate as the monomer. The polymer becomes polymethyl methacrylate, or PMMA, plexiglass, often used in windows. Things get a little bit more complicated when you begin to deal with step polymerization examples. This functional group over here is called an amide. And so the general class of polymers that have this group is polyamide, which will be one of the examples that we will see later on in module 1. An example of this particular polyamide is nylon, polyhexamethylene. Okay, there are 6 methylene groups, adipamide, and it's also known as nylon 6,6. Polyesters, they begin to have the benzene groups not as a side group but part of the main chain. This is polyethylene terephthalate, or PET, and polycarbonate, another transparent polymer.